Normandy coast, 7 June 1944, 0620 hours. A Luftflotte 3 reconnaissance pass returns photographs of Gold and Omaha sectors. The shoreline that was open water on 6 June now shows geometric shadows offshore. Initial captions mark wrecks and hulks. They are not wrecks. They are the first sections of 2 prefabricated harbors towed from southern England and flooded into position. Breakwaters of concrete and steel, floating piers, and hinged roadways designed to take Liberty ships in open water. Allied staff projections for the first 30 days require over 1 million tons landed. German assessments predict collapse without a captured deep-water port. Yet within days, the British Mulberry B at Arromanches is accepting ocean-going freighters. By autumn, the system will handle approximately 2.5 million troops, approximately 500,000 vehicles, and approximately 4 million tons of cargo across the Normandy beaches. Germany prepared to destroy ports. Britain arrived having built its own, and the photographic evidence is already too late to change the campaign. London, 20 June 1942. On a Ministry of Supply desk, the Dieppe raid post-action summaries sit beside inter-service logistics tables. Pre-war doctrine assumed seizing an intact port. Dieppe proves major harbors will be blocked, demolished, or defended to catastrophic cost. Combined operations under Admiral Lord Louis Mountbatten receives the stark projections. Planning models show the first month of a continental campaign needs approximately 1 million tons of supplies plus vehicle throughput beyond what beach landings alone can sustain. Time estimates for port repair are measured in months, not weeks. British memoranda in 1942 through 1943 conclude French ports will be unusable for an extended period after capture and demolition. The Chiefs of Staff Committee reviews options. Engineers from the War Office present calculations. Daily tonnage requirements, tidal ranges, channel weather patterns, and German coastal defenses. Every scenario ends the same: victory requires supply capacity that does not yet exist. The requirement is formalized in writing. Create an artificial harbor that can be installed from the sea, independent of shore facilities. The directive reads, "Bring the harbors with us." Words that trigger the largest single prefabrication effort of the British War. Thousands of workers will be mobilized. Shipyards will be commandeered. Entire coastal towns will become construction sites. And all of it must be completed before any invasion fleet can sail. Admiral Bertram Ramsay, designated Allied Naval Commander-in-Chief Expeditionary Force, studies the proposal. His staff officers calculate tug requirements, towing speeds, channel crossing times, and anchor loads. The numbers are extraordinary. If this works, the force will possess ports before it lands. If it fails, the entire invasion may stall on the beaches. Garleston, Scotland, 14 October 1942. Test cruise in oilskins mark wave heights on the Solway Firth. A floating span flexes under truck load, joints creaking in the cold. Critics expect such structures to fail in Atlantic weather. Early trials prove modular units can survive tidal range and surf if properly moored and hinged. The Royal Engineers Experimental Establishment runs load tests in winter conditions, the worst the channel can offer. Engineer Alan Beckett's flexible whale roadway system uses bolted steel spans with articulation to absorb motion. His Beetle pontoons provide buoyancy and stability. Separately, teams design Phoenix caissons, reinforced concrete structures up to 60 meters in length, displacing thousands of tons. When flooded, they will sink to the seabed, forming a breakwater. Spud pierheads will jack on piles to maintain a constant deck height through the tidal range. Bombardier floating breakwaters will add offshore wave attenuation. The specifications are precise. Load tests rate whale sections to lorry and tank weights with sea states up to moderate gales. Phoenix units must withstand Atlantic swells and maintain structural integrity for months. Spud systems must operate reliably through 12-meter tidal ranges. Every component must be towable at approximately 4 knots and installable by naval crews under combat conditions. The Ministry of Works coordinates across multiple shipyards and civil firms. Concrete suppliers, steel fabricators, and marine engineers receive contracts. Production schedules are set. Quality control inspectors arrive at sites across southern England and Scotland. By 15 May 1943, proven prototypes justify mass orders. What began as experimental designs now becomes industrial-scale production. A temporary harbor now has empirical test data showing port-class performance in open water. The engineering journals record the specifications. Professional societies review the calculations. And deep in secure planning rooms, staff officers begin integrating these structures into Operation Neptune, the naval component of Overlord. The invasion timeline now includes a floating harbor convoy as critical as the assault waves themselves. London, 10 February 1944. A Neptune Overlord board at SHAEF shows tug allocations alongside assault convoys. German analysts expect any Allied offensive to stall on logistics. Allied staff integrates Mulberry into the initial assault plan rather than as a follow-on. The assumption is clear: without rapid port capacity, the invasion collapses. With it, the lodgment grows faster than German reserves can contain it. Brigadier Bruce White, Director of Works, oversees construction across more than 10 coastal sites. Sir William Halcrow and Partners provides engineering supervision. The Ministry of Works coordinates approximately 45,000 workers, contractors, engineers, crane operators, welders, and laborers. Security is absolute. Workers know only their individual tasks. The full scope remains compartmentalized. By May 1944, production is complete. Approximately 300 Phoenix caissons line the southern coast. Approximately 33 pierheads await towing. Approximately 10 miles of whale roadway sit assembled in sections. Tugs receive assignments. Navigation parties train for cross-channel towage at approximately 4 knots. Crews drill scuttle and flood procedures if attacked. Maintenance teams practice emergency repairs at sea. Senior naval memoranda record the judgment that, if successful, the force will possess ports before it lands. The phrase appears in classified correspondence multiple times. It represents a fundamental shift in amphibious doctrine, not capturing ports but manufacturing them. Not relying on enemy infrastructure, but creating British infrastructure offshore. Admiral Ramsay reviews the final towing schedules. Convoy sequences are synchronized with the assault window and meteorology forecasts. 1.5 million tons of concrete and steel now depend on weather, towing schedules, and deception plans to cross under enemy eyes. German reconnaissance flights photograph British coastal waters daily. They report activity but cannot decipher intent. The structures appear too large to hide and too numerous to be mere decoys. Yet no one in German intelligence predicts their true purpose. The invasion date approaches. Tugs take up towing positions. Crews stand ready. And across the channel, German defenders prepare for an assault that will arrive with its own harbors already built. English Channel, 7 to 8 June 1944. Pre-dawn. Tugs shoulder Phoenix silhouettes off Selsey Bill. Navigation lights remain hooded. Speed holds steady at approximately 4 knots. Luftwaffe reconnaissance expects rescue tows of damaged shipping. Instead, organized streams of unarmed, escorted structures proceed on planned tracks. Royal Navy towing groups coordinate over 100 tugs, dozens of barges and escorts, and fuel consumption in the hundreds of thousands of gallons. The convoy organization is meticulous. Each Phoenix caisson is assigned a specific tug, a backup tug, and an escort vessel. Navigation officers plot courses to avoid known minefields and keep formations clear of assault shipping lanes. Weather forecasters provide hourly updates. Towing speeds vary based on sea state and caisson displacement. The largest units, Phoenix caissons displacing over 6,000 tons, require multiple tugs in tandem. Smaller bombardment units tow behind single vessels. Crews have been briefed on scuttle procedures if attacked. German E-boats prowl the channel. Luftwaffe bombers fly sorties against the invasion fleet. Yet the harbor convoys proceed largely unmolested. Allied air superiority suppresses attacks. Naval escorts screen the slow-moving columns. Fighter patrols maintain coverage overhead. Destroyer groups investigate radar contacts. and the massive concrete structures lumber across open water at walking pace. Sailors aboard the tugs work continuous watches. Engine rooms maintain steady revolutions. Tow cables, thick hemp and wire rope under enormous strain, require constant monitoring. A parted cable can send a phoenix adrift into shipping lanes or onto shoals. Deck crews stand ready with backup lines. Navigation teams cross-check positions against pre-plotted waypoints. The crossing takes 30 hours for the lead elements, longer for trailing units. By D-Day +2, arrival begins precisely sequenced sinking of caissons to set the first gooseberry breakwaters off each landing beach. A tug eases a phoenix into position. Survey craft have marked exact locations with buoys. Valves open. Water thunders in. The caisson settles upright, weighted by its own mass, stabilized by its broad base. One after another, the massive concrete structures sink into line. Within 48 hours of H-hour, a harbor's outline stands offshore where no port existed. German shore observers report the activity. Initial assessments label the structures hulks sunk as block ships, a defensive measure to create artificial reefs. The interpretation seems logical. Allied vessels appear to be scuttling damaged ships to form breakwaters. German analysts note the activity but do not grasp the engineering behind it. They see wrecks. They do not see a harbor under construction. Royal Navy beach parties coordinate the complex choreography. Each caisson must be positioned within meters of its planned location. Tidal calculations determine flooding times. Mooring crews set anchors, massive multi-ton ship anchors dragged into position by small craft. And as the breakwaters take shape, bombarding units are positioned offshore to attenuate wave energy. The system is modular, redundant, and designed for rapid assembly under fire. Within days, sheltered water exists where open ocean battered the coast for millennia. Normandy, 8 to 14 June 1944. A phoenix valve opens. Water thunders in. The caisson settles upright on marks previously sounded by survey craft. German shore observers report hulks sunk as blockships. In fact, purpose-built caissons interlock to form a seawall, while floating bombardones reduce wave energy offshore. Royal Engineers No. 1 Assault Brigade and Royal Navy beach parties coordinate placement. United States Navy Seabees and Army engineers work at Omaha. The first whale roadway to a spud pierhead connects within days. Installation crews bolt the articulated steel spans together section by section. Each whale unit, 80 feet long, weighing approximately 100 tons, is floated into position and secured. Hinge joints allow the roadway to flex with wave action without structural failure. Engineers test each connection under load before allowing vehicle traffic. The spud pierheads prove their engineering brilliance. Each pierhead consists of a floating steel platform mounted on 4 vertical legs, the spuds, that slide through the deck on hydraulic jacks. As tide rises and falls across a 12-meter range, the spuds remain planted on the seabed, while the platform jacks up and down to maintain constant height. Lorries roll from ship to shore without interruption regardless of tidal state. The system operates continuously through 6-hour tidal cycles. Handling begins at approximately 1,000 tons per day, scaling as spans are added. Liberty-class freighters tie up in open water and discharge directly to vehicles and DUKW amphibious trucks. Stevedore parties work in shifts around the clock. Cargo nets swing from ship's booms. Forklifts maneuver on the floating roadways. Traffic controllers direct vehicle flows. The pierhead decks, 40 feet wide, accommodate two-way lorry traffic with passing lanes. Official dispatches note caissons holding firm and pierheads stabilizing after initial adjustments. Engineers monitor joint flex in the whale roadways. Strain gauges measure stress loads. Mooring crews check anchor loads daily and adjust cable tensions. Divers inspect underwater connections and caisson bases. Maintenance parties replace damaged sections. The system proves its redundancy. Individual components can be swapped without halting operations. At Arromanches, British Mulberry B takes shape rapidly. The harbor footprint covers approximately 2 square miles of water. 15 Phoenix caissons form the outer breakwater. 23 smaller Phoenix units create inner protection. 6 spud pierheads provide discharge points. 10 miles of whale roadway connect pierheads to shore. 4 bombarding units float offshore, each over 200 feet long, damping swell before it reaches the main breakwater. At Omaha, American Mulberry follows similar construction. Both harbors use identical components: Phoenix, spud, whale, and bombarding. Both operate under fire. German artillery targets the structures from positions inland. Luftwaffe bombers make low-level attacks. Oerlikon 20mm mounts clatter from pierheads as bomb carriers skim at mast height. Yet the harbors continue to function. A deep-water anchorage has been created with no quay walls, docks, or cranes on land. Throughput increases daily. The first week sees approximately 1,000 tons per day. The second week doubles that figure. By mid-June, both artificial harbors are handling more cargo than any beach operation could sustain. Supplies flow directly from ships to inland depots. Ammunition, fuel, rations, vehicles, and reinforcements move across floating roadways in a continuous stream. The lodgement expands, and Germany begins to realize the scale of what has appeared offshore. Normandy, 15 to 18 June 1944. Oerlikon 20mm mounts clatter from pierheads as bomb carriers skim at mast height. Maintenance crews tighten bolts on swaying whale joints. Adversaries assume the complex will be fragile under air attack. Modularity and redundancy permit rapid replacement of damaged sections. Naval construction and maintenance parties work around the clock. Royal Engineers roadway details replace damaged Beetle pontoons. Beach anti-aircraft detachments engage low-level attackers with automatic weapons and light flak. The Luftwaffe attempts concentrated strikes on 16 June. Junkers Ju-88s approach at low level, hoping to skip-bomb the pierheads. Fighters intercept most attackers before weapons release. Those that penetrate face murderous fire from ships, beach batteries, and the pierheads themselves. 2 bombs strike whale sections at Mulberry B, destroying approximately 160 feet of roadway. 1 caisson sustains damage from a near miss. 3 bombarding units are holed. Interchangeable components prove their worth immediately. Spare whale spans are held on station aboard supply vessels. When the bomber scores direct hits, destroying sections of roadway, replacement units arrive within 6 hours. Crews unbolt the damaged spans using pneumatic wrenches. Tugs tow wreckage clear. Fresh sections are floated into position and bolted down. Within 18 hours, traffic resumes. Repair cycles are measured in hours, not days. The damaged caisson is patched by diverse using underwater concrete. The bombardones are hauled out, welded, and refloated. Anchoring geometry is adjusted based on service observations. Engineers calculate that mooring loads exceed initial predictions during storm conditions. Additional anchors are set. Cable arrays are reinforced with redundant lines. Caisson spacing is optimized based on measured wave patterns. The system adapts to real-world conditions. Every lesson learned during operations is immediately applied to subsequent construction. Despite damage to several caissons and pierheads, daily tonnage rises toward double initial figures. By 18 June, Mulberry B at Arromanches is handling approximately 2,000 tons per day. Mulberry A at Omaha achieves similar throughput. The harbors prove resilient beyond design expectations. Under fire and in motion, a port keeps time, its throughput increasing rather than collapsing. German commanders receive intelligence reports describing the structures. Field commanders observe supply vessels discharging at sea. Reconnaissance aircraft photograph the installations. Intelligence assessments revise earlier judgments. These are not block ships. These are not improvised jetties. These are engineered harbors, prefabricated in Britain and installed in open water. The recognition comes as a shock. Wehrmacht staff officers who reviewed pre-invasion intelligence now confront a capability no one predicted. The artificial harbors represent industrial organization and engineering ambition on a scale German planning never anticipated. The realization comes too late to mount effective countermeasures. Allied air superiority prevents concentrated bombing raids. German naval forces cannot penetrate the invasion fleet screens. Artillery fire from shore batteries causes damage but cannot halt operations. The harbors continue to expand. Additional Phoenix units arrive daily. More whale spans are connected. Berth capacity increases. Throughput continues to climb. And then, on 19 June, the weather changes. English Channel, 19 to 22 June, 1944. Barometer drops sharply. Swell builds beyond design day profiles. Mooring cables sing under strain. A summer gale is expected but not at prolonged intensity. Wind speeds exceed 30 knots by 19 June afternoon, reaching 40 knots by evening. Wave heights reach 4 to 5 meters, occasionally peaking at 6 meters. Tidal surges add stress to mooring systems already loaded near capacity. The artificial harbors face their first major test, not from enemy action, but from the channel itself. Meteorologists track the storm's development. The system originates in the Atlantic, deepens rapidly, and stalls over the channel. Forecasters predict 3 days of gale-force winds. Harbor commanders order emergency preparations. Ships at anchor move to deeper water. Vessels alongside pierheads cast off and stand out to sea. Maintenance crews secure loose equipment. Mooring parties add extra anchors and cables where possible. And the structures brace for impact. At Omaha, Mulberry begins to break apart within 24 hours. Pierheads part moorings as anchor cables snap under cyclical loading. Whale spans tear free and collide, steel grinding against steel. Phoenix caissons, designed for moderate seas, not prolonged gales, shift position under repeated wave impacts. Some caissons crack. Others tilt as seabed foundations scour. Bombardment units break loose and drift, creating navigation hazards. United States Army and Navy engineering logs record desperate salvage efforts. Crews work in dangerous conditions to save critical sections. Tugs attempt to re-anchor drifting components. Divers go down in heavy seas to assess underwater damage. But the violence of the storm overwhelms all efforts. Wave action destroys whale connections faster than they can be repaired. By 21 June, multiple pierheads are adrift or collapsed. By 22 June, Mulberry is written off. Components are scattered across miles of ocean. Some are driven ashore. Others sink in deep water. The American artificial harbor is a total loss. At Arromanches, Mulberry B sustains damage but remains structurally serviceable. British records show reinforced mooring arrays and different Phoenix orientations contributed to survival. The caissons hold position through the storm. Engineers had angled some units to deflect wave energy rather than absorb it head-on. Additional mooring redundancy prevents cascading failures when individual cables part. Pierheads remain operational despite violent motion. Crews lash down everything movable. Whale roadways flex dramatically, articulated joints working exactly as designed but do not break. The system survives. Crews make emergency repairs as conditions allow. Damaged cables are replaced. Shifted caissons are resurveyed and accepted in new positions. Cracked concrete is patched. When the storm passes on 22 June afternoon, the harbor remains functional. Throughput resumes within hours. Ships return to berths. Lorries roll again across whale spans. The damage is reparable, not catastrophic. The measured impact is stark. Mulberry is gone. American effort shifts entirely to open beach logistics. Omaha becomes a vehicle and supply beach with no protected anchorage. Mulberry B becomes the critical lifeline for the entire lodgment. All subsequent British landings, and a significant portion of American supply, will flow through Arromanches. The storm removes one artificial port, turning the other into the decisive logistics instrument of the campaign. A natural disaster has determined strategic outcomes. The channel itself has reshaped the invasion plan. Arromanches, July to September 1944. A Liberty ship eases inside sheltered water. Spud pierhead decks maintain level as tide falls. Lorries roll continuously along whale spans, tires drumming on steel roadway. Design targets are exceeded from the first week of full operations. Routine throughput reaches approximately 7,000 tons per day. Peak days exceed approximately 18,000 tons as additional berths and roadways come online. The harbor operates at industrial scale. Royal Army Service Corps Traffic Control coordinates movements with military precision. Each ship receives a berth assignment before entering the harbor. Discharge priorities are set based on operational requirements: ammunition first, then petroleum oil lubricants, then rations and equipment. Beach groups manage loading zones. Military police direct vehicle flows. Signs in English mark routes from pierheads to inland dumps. Integration with PLUTO feeder lines begins in July, delivering large volumes of petrol directly to forward depots. The pipeline under the ocean system pumps fuel from England to Normandy through underwater pipelines. Mulberry B becomes the primary distribution point. Tank farms are established inland. Fuel convoys move continuously from harbor to front. By August, PLUTO delivers over 1 million gallons per day, enough to sustain mechanized operations across the entire lodgement. Spud jacking systems ride the tidal range without interruption. Each 6-hour cycle sees the platform rise or fall 12 meters while maintaining perfect horizontal level. Hydraulic pumps operate continuously. Maintenance crews grease jacking mechanisms and inspect guide rails. The pierheads prove more reliable than conventional fixed docks. No waiting for tide. No height adjustments. No gaps between ship and shore. Standardized convoy turnarounds keep ships moving efficiently. A Liberty ship berths, discharges cargo in 8 to 12 hours, and departs. Stevedore gangs work in 3 shifts. DUKW amphibious trucks shuttle between pierheads and beach dumps, carrying 3-ton loads. Larger lorries take priority cargo directly to inland depots. Traffic flows around the clock. At night, shaded lights illuminate working areas without providing aiming points for enemy aircraft. Priority lanes separate ammunition, petroleum oil lubricants, and engineer stores. Explosive cargoes move on dedicated roadways with extra spacing. Fuel tankers use separate berths. Vehicles and heavy equipment discharge at specialized pierheads with reinforced decking. The system sorts and routes cargo with commercial port efficiency, except this port is made of floating steel and operates under fire. The artificial harbor offsets Cherbourg demolition damage. German engineers spent weeks preparing Cherbourg for destruction. When Allied forces captured the port on 26 June, they found systematic ruin. Harbor facilities demolished. Cranes toppled into basins. Quays cratered by explosives. Minefields in approach channels. Block ships sunk in navigable waters. Lock gates destroyed. Rail yards wrecked. Repair estimates ran to months. United States Navy and Army engineers work desperately to restore Cherbourg. Divers clear block ships. Minesweepers sweep channels. Construction battalions rebuild quays. Cranes are salvaged or replaced. By late July, limited operations begin. By August, Cherbourg handles growing tonnage. But throughout the critical summer, Mulberry B sustains the buildup while engineers work to restore conventional port capacity. Operations Goodwood and Cobra depend absolutely on continuous supply. British armored offensives east of can consume ammunition at extraordinary rates. Thousands of shells per day for sustained bombardments. American breakout operations demand fuel for mechanized columns racing across France. Hundreds of thousands of gallons daily. The tonnage flows through Arromanches without pause. Vehicle parks expand inland. Ammunition dumps grow to cover acres. Fuel depots multiply, and the front line advances. German plans assumed weather plus ruins equals paralysis. Instead, an enemy lands freighter loads as if into a civilized port. The strategic calculation has failed completely. Germany prepared to defend ports. Britain manufactured one offshore. The differential in logistics capacity now determines operational tempo more than tactical engagements. Allied divisions move when supplied. German formations remain static for lack of fuel and ammunition. The war shifts at the speed of the supply column, and the Allied column does not slow. Paris, Luftflotte 3 Headquarters, 5 to 20 July 1944. Interpreters slide stereoscope frames showing concentric lines off aeromanches. And analysts pencil notes artificial mole? Initial assessments label the features sunk shipping. Photo interpreters trained to identify vessels struggle with structures that fit no existing classification. The geometric patterns suggest organization, but the scale seems impossible. Subsequent summaries acknowledge engineered structures, but by then Allied landings have surpassed approximately 1 million tons ashore. Daily reconnaissance flights photograph the harbors from varying altitudes and angles. Intelligence officers compare images across multiple days. The structures are not sinking. They are not degrading. They are expanding. New sections appear overnight. Berthing capacity increases. Ship traffic intensifies. The photographic evidence accumulates. On 10 July, a revised assessment concludes that the Allies have installed prefabricated harbor facilities of unprecedented scale. The recognition lag is measured in weeks. Intelligence reports revise daily. Initial confidence that the structures are improvised defenses gives way to grudging acknowledgement of sophisticated engineering. By 15 July, Luftflotte 3 forwards detailed analysis to Oberkommando der Wehrmacht. The reports describe floating piers, adjustable decking, concrete breakwaters, and coordinated logistics operations. Tonnage estimates based on observed ship movements alarm German staff officers. But understanding comes too late for countermeasures. German naval intelligence adds its assessment. Kriegsmarine analysts recognize the harbors solve the port problem that was supposed to cripple the invasion. Pre-invasion German planning assumed Allied forces would require a major port within days or face supply collapse. The artificial harbors invalidate that assumption. Margin calculations showed that beach logistics alone could not sustain forces beyond 2 weeks. The Mulberry Harbours extend that indefinitely. Allied air superiority suppresses attack sorties against the harbors to negligible numbers. Luftwaffe bombers attempting raids face massed anti-aircraft fire and fighter interception. On 12 July, 6 Ju-88s attack Mulberry B. 4 are shot down by Spitfires before reaching the target. 2 deliver bombs, both miss. On 18 July, a night raid by Heinkel He-111s places several bombs near Phoenix caissons. Damage is minimal. Repairs are completed by dawn. Surviving missions report hits on structures, but daily reconnaissance shows the harbors still functioning. Damage is repaired faster than it accumulates. Claims of harbor destroyed appear in German mission reports. Subsequent photographs contradict those claims. Operations continue. Ships still arrive. Cargo still moves. The disconnect between reported bomb damage and observed operational status frustrates German commanders. The inability to mass air or naval strikes removes the last German opportunity to contest the buildup at the shoreline. Kriegsmarine forces are bottled in French Atlantic ports or destroyed attempting sorties. E-boats operate from channel ports but cannot sustain campaigns against defended anchorages. Torpedo attacks are attempted. Most are driven off by escorts. Those that penetrate face layered defenses, destroyers, patrol craft, and coastal batteries. 2 E-boats are sunk attempting attacks on Mulberry B. No significant damage is achieved. Coastal artillery fire causes casualties and damage but cannot halt the flow of supplies. German batteries shell the harbors when Allied counter-battery fire permits. Rounds impact Phoenix caissons, creating craters and spalling but not breaching the massive structures. Pierheads are hit occasionally. Maintenance crews report shell damage, make repairs, and resume operations. The harbors operate under fire and continue to expand capacity. By late July, Luftflotte 3 assessments admit the presence of large-scale artificial port facilities functioning as major harbors. The reports detail observed components: floating roadways, concrete breakwaters, adjustable piers, fuel lines, and organized shipping lanes. Analysts estimate throughput capacity based on observed ship movements and vehicle traffic. The figures are alarming. Germany faces an enemy that landed with fully functional ports and has sustained a massive offensive without capturing a single major harbor intact. The strategic implications are clear and devastating. The invasion cannot be starved out. Beach defenses failed to prevent landing. Port denial failed to prevent supply. and the artificial harbor proves immune to the disruption strategies Germany employed successfully in other theaters. The enemy eventually identifies a moving harbor, but cannot meaningfully strike it. Recognition without response defines German intelligence in Normandy. By the time the structures are understood, the campaign is already decided by the tonnage they delivered. The photographic evidence documents not just a harbor, but the collapse of German strategic planning. Normandy, August 1944. A quartermaster board tracks daily consumption. Ammunition, petroleum oil lubricants, rations, vehicle parts, medical supplies, signal equipment. Figures rise with the pace of operations. German formations expect Allied supply fracture without a major port. Allied daily consumption, approximately 12,000 tons per day for the entire Normandy group, remains met by combined Mulberry, Beaches, and Cherbourg as repairs progress. The logistics balance sheet tells the unambiguous story of the campaign. Mulberry B contributes a significant share, often cited at roughly one-third of tonnage during key weeks in July and August. Combined with open beach operations and the gradual restoration of Cherbourg capacity, Allied supply exceeds consumption by comfortable margins. Stockpiles grow rather than shrink. Reserves accumulate in depot areas. Forward dumps expand. The offensive does not pause for logistics. Supply convoys reach frontline units on schedule. Ammunition expenditure is unrestricted. Fuel allocation is generous. Food rations remain full. German 7th Army and Panzer Group West intake through bomb-damaged channel ports and rail lines remains far lower. Fuel shortages constrain panzer operations. Ammunition deficits limit artillery responses to Allied attacks. Rations are reduced. Medical supplies run short. Replacement parts are unavailable. The logistical strangulation is gradual but relentless. Studies and captured reports note vehicles abandoned for lack of fuel before key operations. 2nd SS Panzer Corps reports tanks rendered immobile in late July. Units receive orders to attack but cannot comply. Fuel tanks are empty. Panzer divisions report average operational readiness at 50%, then 30%, then lower. Infantry divisions ration rifle ammunition. Machine gun crews conserve belts. Artillery batteries conserve shells, firing only when targets are certain. Mortarmen count rounds. The contrasts are stark and measurable. Allied formations advance with full tanks and overflowing ammunition trucks. Resupply convoys arrive nightly. Soldiers receive mail, cigarettes, and hot food. Wounded are evacuated rapidly. Replacements arrive to fill casualties. Equipment is maintained to high standards. German formations dig in and wait for supplies that never arrive in sufficient quantity. Ammunition expenditure is restricted. Fuel allocations are cut. Rations are reduced to below sustainment levels. Wounded accumulate in aid stations. Replacements do not arrive. Equipment breaks down and cannot be repaired. The logistics gradient, sustained by a manufactured port, tilts combat outcomes irrespective of tactical engagements. Superior German tactical performance cannot overcome logistics deficits. Well-trained units cannot fight without ammunition. Experienced commanders cannot maneuver without fuel. Defensive positions cannot hold when resupply fails. The material balance determines outcomes more than courage or skill. Operational linkage is direct and documented. When British 2nd Army launches Operation Goodwood on 18 July, approximately 2,500 tons of ammunition are expended in the opening bombardment alone, roughly equal to total German ammunition supply for the entire Normandy front that week. The supply chain sustains the British effort without pause. Guns fire until barrels overheat. Fresh ammunition arrives before stocks deplete. The offensive continues for 3 days at extraordinary intensity. German counterattacks stall for lack of fuel and shells. Panzer reserves ordered to block the offensive move at walking pace to conserve diesel. Artillery support is minimal. Batteries have 20 to 30 rounds per gun. Infantry units defend with automatic weapons ammunition rationed to short bursts. The defensive effort collapses not because positions are overrun, but because sustainment fails. Allied mechanized columns advance at speed, supplied continuously from Arromanches and the beaches. Fuel convoys keep pace with spearheads. Ammunition trucks follow assault formations. Supply dumps leapfrog forward as territory is captured. The logistics train functions at industrial scale and tempo. German commanders watch Allied vehicles advance knowing their own forces cannot respond. Fuel tanks are empty, ammunition lockers are bare, and the supply system has failed. The front line moves at the speed of the supply column. The Allied column does not slow. German formations retreat not because they are defeated tactically in isolated engagements, but because they cannot sustain defense without supply. Positions are abandoned when ammunition runs out. Strongpoints fall when defenders cannot be reinforced. And the Normandy campaign becomes a pursuit as German armies withdraw eastward, harassed constantly by forces that never outrun their logistics tail. Victory is manufactured in concrete and steel as much as won in combat. The artificial harbor sustains an offensive that German planning assumed impossible. London, 10 September 1944. A briefing in the cabinet war rooms tabulates cumulative landings of personnel, vehicles, and tonnage attributable to Mulberry operations and beaches. Pre-invasion doctrine argued only captured ports could feed an army. Post-invasion data shows a purpose-built artificial harbor sustained the decisive phase until major ports reopened. The numbers rewrite amphibious operations planning for the remainder of the war and beyond. Approximately 2.5 million personnel passed through the Normandy beach and harbor system between 6 June and late November. Approximately 500,000 vehicles, tanks, lorries, jeeps, artillery pieces, and specialized equipment landed and moved inland. Approximately 4 million tons of supplies sustained continuous operations across 5 months. Mulberry B handled a significant share. Estimates range from 1/4 to 1/3 of total tonnage during the critical summer months when Cherbourg remained under repair. The artificial harbor proved decisive. Allied commanders acknowledge in dispatches the surprise of an enemy harbor that arrived with the fleet. General Dwight D. Eisenhower's staff reports credit Mulberry with enabling the lodgment to expand faster than German reinforcements could contain it. British 21st Army Group reports note that without the artificial harbor, operations would have stalled awaiting Cherbourg repairs. United States 1st Army reports acknowledge Mulberry B sustained much of American supply after Mulberry A's loss. German post-war debriefings of senior officers record similar reactions. Field Marshal Gerd von Rundstedt's staff reported shock at the scale and speed of Allied logistics. Commanders expected port denial to cripple the offensive for weeks or months. The assumption was fundamental to German defensive planning. Without ports, the Allies could not sustain forces beyond a narrow beachhead. With ports, they could expand the lodgment indefinitely. The artificial harbors removed German control over that equation. Generals expected Allied supply to fracture. Instead, the British manufactured a port offshore and operated it under fire for months. German intelligence had detected unusual construction activity in British coastal waters during spring 1944. Reconnaissance photographs showed large structures under assembly. Analysts speculated about anti-submarine barriers, artificial islands for air defense, or floating fuel depots. No one predicted prefabricated harbors capable of handling Liberty-class freighters in open water. The strategic assumption that ports are fixed, vulnerable, and irreplaceable proved false. Harbors could be manufactured. Ports could be mobile. Logistics infrastructure could be independent of shore facilities. The implication extended beyond Normandy. Future amphibious operations would not depend on capturing ports intact. Attackers could bring their own harbor capacity and install it offshore. The defenders' advantage of controlling ports evaporated. Industrial organization on an unprecedented scale made Mulberry possible. Thousands of contractors worked under centralized materials control. Civil engineering firms coordinated with naval architects. Shipyards fabricated components to tolerances measured in millimeters across structures displacing thousands of tons. Shared naval civil engineering practice produced wartime infrastructure at speeds peacetime projects could not match. 45,000 workers built components across southern England. Coordination extended from design offices in London to coastal fabrication sites to towing convoys to assembly crews offshore Normandy. Security compartmentalization prevented leaks. Industrial mobilization delivered on schedule. Quality control ensured reliability. And logistical planning synchronized delivery with the invasion timetable. The system worked because every element — design, production, transport, installation, operation — was planned and executed with precision. The core of the Normandy victory is recast as an engineering and logistics success as much as a tactical one. Historians later note that Operation Overlord succeeded because Allied planners solved the port problem before the invasion rather than after. The decision to manufacture harbors, rather than capture them, removed German control over the single most vulnerable aspect of amphibious assault: supply. The beaches became the ports. And the ports became mobile, reparable, and immune to pre-planned demolition. In 1944, the key Allied weapon in Normandy is a civil-engineered system scaled to military use. Not a tank, not a bomber, not a rifle, a harbor, built of concrete and steel, towed across the channel at 4 knots, assembled under fire, and operated continuously until traditional ports could be restored. Strategy redefined by engineering. Victory manufactured before the first shot was fired. Arromanches, November 1944. Final lorries roll down whale spans. Maintenance crews unbolt sections for redistribution. Caissons remain as seawalls. Designed for a short operational window, components outlast the planned schedule by months. With Antwerp opening in late November after extensive mine clearance, Mulberry B stands down after continuous service. The operational life exceeded expectations. The throughput exceeded projections. And the strategic impact exceeded all pre-invasion estimates. Totals, as commonly cited in post-war summaries, are extraordinary. Approximately 2.5 million personnel passed through the Normandy beach and harbor system. Approximately 500,000 vehicles landed and moved inland. Approximately 4 million tons of supplies sustained the campaign from June through November. Mulberry B handled a significant share. Estimates range from 1/4 to 1/3 of total tonnage during the critical summer months when Cherbourg remained under repair. Resources shift to restored ports. Antwerp becomes the primary logistics hub for operations into Germany. Cherbourg returns to full operation. The artificial harbor is decommissioned according to plan. Whale roadways are disassembled and relocated to other theaters where similar systems might be needed. Spud pierheads are towed away for potential reuse. Bombardones are salvaged for scrap metal. But the Phoenix caissons remain. Too massive to move economically, they are left in place. Several units continue as coastal defenses for decades. Others serve as breakwaters for fishing fleets. The remains at Arromanches become a physical archive of wartime engineering. Tourists walk the beaches and see concrete structures offshore. Interpretive markers explain their purpose. Museums display components. And the town itself becomes synonymous with the artificial harbor that made history. A purpose-built weapon of logistics transitions into civilian infrastructure and historical evidence. The structures that won a campaign now serve peacetime purposes, protecting harbors, sheltering boats, and reminding visitors of what industrial democracy achieved under pressure. Legacy in situ proves durable. 70 years after D-Day, Phoenix caissons still stand off Arromanches. Concrete eroded by decades of tides and storms, but foundations intact. Engineers study them. Historians photograph them. And veterans return to see the structures they helped install under fire in June 1944. Europe and United Kingdom, 1945 to 1950. Professional engineering journals and official histories compare Mulberry's daily capacities with European commercial ports. Few pre-war planners conceived an artificial harbor matching major port throughputs. Evaluations judge the project among the most successful temporary works of the war. The Institution of Civil Engineers publishes proceedings. The Royal Engineers document lessons learned. The United States Army Corps of Engineers studies the system for future amphibious operations. Allied engineering divisions credit Mulberry with enabling the operational tempo before large ports came online. Without the artificial harbor, the Normandy lodgment would have depended entirely on open beach logistics and the race to capture and repair Cherbourg. Beach operations alone could not have sustained the forces required for breakout. The harbor gave commanders freedom to build combat power faster than German reserves could contain the invasion. Time bought by Mulberry allowed the accumulation of forces necessary for operations in late July and August. German post-war analyses acknowledged the surprise and strategic effect. Interrogations of Wehrmacht officers reveal consistent underestimation of Allied logistics capability. German planning assumed port denial would cripple or delay the offensive for weeks or months. The appearance of functional harbors offshore, immune to pre-planned demolitions, invalidated those assumptions completely. Several German generals noted in memoirs that the artificial harbor represented a level of industrial coordination and engineering ambition they had not anticipated from any military power. The Normandy campaign becomes a case study in logistics over doctrine. Pre-war amphibious theory emphasized rapid seizure of ports. Overlord demonstrated that ports could be manufactured and installed faster than existing facilities could be captured and repaired. The lesson influenced post-war planning profoundly. Future amphibious operations incorporated floating pier systems, prefabricated harbors, and mobile logistics infrastructure. The principle, bring your own port, became standard doctrine for the United States Navy and Marine Corps. Cause and effect remain clear in historical analysis. Strategy was redefined by engineering. Civil-military industrial coordination determined victory as much as battlefield tactics. And the Normandy campaign proved that free peoples, possessing will and industrial means, could overcome prepared defenses through innovation and organizational capacity. Victory ashore in 1944 was manufactured long before, cast in concrete, bolted in steel, and towed into battle as Britain's own moving port. Mulberry was an engineered answer to a strategic problem. Land fast, sustain faster, and do so without relying on intact ports. Tested in Scottish waters, built by tens of thousands across British works, towed at walking speed under enemy reconnaissance, assembled under fire, and surviving a major gale, the system kept the Allied advance supplied until continental ports reopened. The decisive numbers, personnel, vehicles, and tonnage were the outcome of design choices, industrial scale, and disciplined maintenance at sea. Germany prepared fortresses. Britain built harbors and brought them across the Channel. In the contest between fixed defenses and mobile logistics, logistics won. What is your perspective on this part of history? Share your thoughts in the comments, because every memory and reflection helps keep the past alive.